Hello grade 11s, you're going to be learning about arithmetic series today. There's a starter question at the top of page 18 which I'm hoping you've already taken a look at. So here it is. We're looking at running each day during a week and the distance of the run is provided by a formula where n represents the day of the week with 1 being Monday. So to find the total distance that I run in a week, of course, we're going to have to substitute into that formula. So when n is 1 on Monday, I will get 2 times 1 plus 3 is 5. So that's Monday's run. And then I can go and work out Tuesdays, and Wednesday, Thursday, Friday, and let's include the weekend as well, shall we? Okay, and of course, we can add all of that up using our calculator, and what will we get? I believe 77. What are we running? We could be optimistic and say that we run 77 kilometers. It probably sounds better than running 77 meters. So what we have just done here is we've actually added up terms in a sequence, and this idea of finding the sum of a sequence has a name, and it is finding it's a series. And we generally use the symbol S for series, and we can say how many terms in the sequence we're adding up. So we could say S7 equals 77. An alternative way of writing it is using sigma notation. So this is the capital Greek letter sigma, and it's meaning that we're going to have to add things up. And you can see that there's some notation below and above. And after it is our expression, very similar to here, Tn plus 3. You can see other variables used. We could have seen n or r are also quite commonly used. The value below is saying which number we're going to start substituting, and the value above is where we're going to end. So this is meaning we've got our expression, and we're going to substitute values of I starting with 1 and counting up to 7, and we're going to add each of those up. And of course we could work all of this out by substituting and adding. So we could work out when r is 1, I'd get 2 minus 1, and then I could add when r is 2 and 3 and 4, and I'm going up to 5 here. Okay, and I would get 25. We can also use our calculator to calculate this for us. So to find the symbol, we go down here where we look for fractions generally. There's lots of useful things here. The one we're after is down there. So I don't really care what letter that is, as long as it matches the letter in my expression. So I'm going from 1 up to 5, and I have an expression which is 2 r minus 1. Our calculator is using x, but as long as they match, it's not an issue. And there we go, we get 25. Okay, and we could evaluate the second one using the same idea. So x equals 1, going up to 4, and this time here's our expression, 12 divided by 2 to the power of, oh, sorry, I've not been looking at what my calculator's doing there. Let's try that again. So 4, and then let's put a fraction in straight away, 12 over 2 to the power of x. That looks a bit better. And there we go, 11.25. So very useful feature on our calculator. So let's look at this idea of a series a little bit more. Pause the video and have a go working through this investigation. It is probably an idea you've looked at in the past when you've been talking about patterning. Hopefully you've had a chance to work through this, and I'm sure you've seen this before and you remembered the idea of pairing up terms in the sequence. So taking the first and the last term, they add up to 101, taking the second term and the penultimate term and realizing that they add up to 101, and so on. So really all this comes down to is saying, well, each pair is worth 101, and if I had 100 terms, that means I've got 100 divided by 2 pairs. I've got 50 pairs. So the calculation becomes much quicker then. Let's try and formalize this and link it a bit more to our work we've done so far on arithmetic sequences. I'm going to change the letters. We've been using U's instead of A's for this, so we'll stick with U's. So what we can do then is we can say we took the first term, U1, and the last term. We'll call that UN if we've got n terms. And that gave us the 101. So now we need to find the 50. And the way we did that is we said, well, there were 100 terms, and we halved it. So I'm going to say I've got n terms divided by 2. So there we go. We've got a formula for our series. This is useful if we know the first term and the last term. It's not so useful if we just know the first term and how a sequence is progressing. But you'll remember from our last lesson, we were using this formula, n minus 1d. So this gave us, this is a way of calculating the nth term in a sequence. So what we can do, if we don't know the last term, is we can substitute this in. So n over 2, u1 plus, and then instead of un, I'm going to write all this out. And hopefully you've already noticed that we'll be able to do a very simple bit of simplification here. We'll just add those two together. 2u1 plus n minus 1 lots of d. Okay, there we go. We've got two formulas. We've got this one, which is useful if we know the first and last term. And we have this one, which is a bit more cumbersome, but if we don't know that last term, is more helpful. Both of these are in your formula guide. You do not need to learn how to, you do not need to memorize them. You just need to learn how to use them. So let's now take a look at an example which tries to pull together as much of this as we can. I'm going to leave the first example for you to try. I think you should find it fairly straightforward, but let's take a look at the second. We're first asked to write down the sum of the first n terms of this series using sigma notation. So we want the first n term. So we're starting with the first term and going up to the nth term. All we need now is an expression for the sequence that starts 2, 6, 10. From all your experience doing patterning through the MIP, you should be able to spot 4i minus 2 is a suitable expression. Alternatively, you've got the formula guide, and you can use that formula. It looks slightly different to the kind of more intuitive expression, but it is equivalent. Okay, so either of those would be fine. Next, find how many terms are needed for the sum of the series to be greater than 1,000. So we can use this formula that we've just got, and what we're looking for is for it to be greater than 1,000. And we're told to use the formula and the table function on our calculator. So I'm in the function app. Oops. What's going on here? So I'm in the function app and I need to enter this. Now remember it's in the toolbox. Right, I have two different letters here, and obviously if I use this variables button, I'll get the same for both of them, which I don't want. What I want to find is the value of x, the value of n we need to get up to 1,000. So that is going to be my x. The other variable can be anything that matches. If you want to, you can use I. I'm just going to use A. So A is 1, and then I'm going to put this expression in. So using A, making sure that that matches matches up, times 4. Okay, now I can go to the table. And if we check when we add up to the first term, we get 2. When we add up to the second term, we get 8, which makes sense. 2 plus 6 is 8. And the third, 18. Yep, when we add on the 10, that makes sense. So what I want to find is how many terms we need to get to above 1,000. I need 23 terms. So what would be sensible is to just draw out a couple of the results. So I'll do one below and then the one we want. So when it's 22, I get 968. When it's 23, I get 1058. So how many terms are needed? 23 terms.